ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 24, mechanical measurements. We have been looking at measurement of pressure and various aspects have been covered already. The present lecture we look at the transient response of pressure measuring devices. So, what we will do in this lecture is to look at how the pressure transducers respond to pressures which are varying with respect to time. We will use the concept of coupling resistance to characterize the connection between the pressure point or the point at which pressure has to be measured and the location of the transducer. Normally, the transducer is far away from the place where the pressure is being fed into it. So, the resistance of the tube through which this pressure has to propagate or the pressure information has to propagate is going to come into picture. So, it is similar to, if you recall what we did when we were talking about measurement of temperature, we talked about the resistance to heat transfer between the system and the surroundings, and this had something to do with the convective environment in which the system is located. Analogous to that, in that case we had a thermal resistance or flow of heat between the system and the surroundings, and that decided what was going to be the response time of the system. In an analogous fashion, in the case of pressure transducers, the connecting line between the point of measurement of pressure and the location of the pressure transducer is going to be an important factor. The shorter the length, the faster is going to be the response. That very easily which can be seen. Anyway, we are going to look at some of these issues as we go along. So, the coupling resistance is like the convective resistance or the film resistance in the case of heat transfer from a system to surroundings. And then of course, there is an inherent inertia of the system, like the mass specific product for a thermal system. The pressure transducer also has got an inertia. So, we are going to look at some of these issues and find out how to discuss or how to characterize the time response of various systems. And what I am going to do is going to take 2 or 3 examples. One is the U-tube manometer, which is a very simple system, but from the point of view of transient, it is more complicated than the other two. Then we are also going to take a look at displacement element type, and thirdly we are going to take a force balance type. These have been already looked at purely from the point of view of operation earlier. We are going to look at the transient behavior of these systems also, and we will follow it up with an example or two depending on the time available. As I mentioned in the previous lecture itself, pressure transients occur in practice in many measurements. The pressure which we are going to measure is going to fluctuate in time or vary with respect to time. An example would be the pressure inside a cylinder of an internal combustion engine as an example. The pressure is continuously going to vary as the piston undergoes the various strokes, and if you pick up the pressure within the cylinder using a transducer and plot it as a function of the location or the position of the piston, you will get the pressure displacement diagram, which is like the PV diagram, which is familiar to us in thermodynamics. So, that is an example where I would be interested in finding out or measure a pressure which is varying with respect to time. Depending on the speed of the engine, this variation could be very fast, or if it is idling, for example, it could be a slow variation. When it is running at a higher speed, the variation is going to be more rapid. There may be many other examples where pressure variations are going to be present, and we want to measure them. Or for example, you take the case of simplest case which I talked about is the U-tube manometer, and you are going to connect it to the pressure which I want to measure, and suppose the pressure fluctuates or varies from a low level to a high level. So, the pressure is going to vary from a low level, and suddenly we change the pressure to a high level. Then the U-tube fluid within the U-tube is going to follow the pressure which is imposed on it and possibly goes into oscillations. So, we will look at some of these things in the present lecture. So, the nature of this response depends on in the case of U-tube manometer, we are going to look at the various forces which are going to be coming into the picture and how the balance is going to be achieved. So, the important thing to remember is that the coupling element and the resistance of the coupling element is one of the important factors which is going to come into the picture. And in the case of U-tube manometer, there is no coupling resistance as it by itself, but there is a resistance to the motion of the fluid within the U-tube itself. So, it is an internal resistance we are talking about. The methodology of looking at the resistance is similar in all the cases, and so what we will do is to look at the coupling element to start with. As I have indicated here, usually process pressure signal is communicated between the measurement point and the transducer via tube. It may be a tube which is a metallic tube, or it could be a tube made of some plastic material like Tygon. The tube may be very small, very short, very large. It can have different diameters and so on and so forth. So, how are we going to model the flow within the tube? That is the question we are going to ask. And what we notice is that the tube element, as you see in the slide, the tube element imposes a resistance due to viscous friction. All fluids have viscosity, and when the fluid moves through the tube, it is going to experience a resistance to motion, which is because of the viscosity of the fluid. So, these are normally modeled using a laminar fully developed flow assumption, which is justified by noting that the fluid motion within the tube is relatively at slow velocity. Most applications going to be very slow velocity, and if you were to calculate the Reynolds number based on the mean velocity of the fluid inside the tube, it will be in the laminar regime. So, that is the assumption we are going to make. So, let us look at the way we are going to model this. So, we are going to borrow some results from laminar viscous flow theory, and in your fluid mechanics course you would be either you would have learned already or you would be learning this later on. But what we will do is we will only take the important results from the laminar viscous flow theory and then use it for our purpose. So, here I have shown a tube which is a circular cross section tube. So, this is the tube I am talking about, and the fluid flow is taking place from left to right. It enters here and goes out from the right side. If the tube is long enough, the velocity profile inside the tube or the variation of velocity within the tube because of laminar viscous flow will be what is called fully developed. That means that the shape of the velocity profile is not going to change along the length of the tube. It is going to remain the same, and of course, the same amount of fluid is moving across from the left to right. So, the velocity profile totally is unchanged as the fluid progresses along the length of the tube. As the flow takes place from right to left to right, the flow velocity variation with respect to the radius in the radial direction remains the same. And this velocity profile is given by what is called a parabolic velocity profile, which is indicated by parabola here. The velocity is 0 at the walls and a maximum at the center line or the axis of the tube. I can in fact calculate based on the mass flow rate, I can replace the velocity profile which is parabolic by a mean velocity, which will be a rectangular profile. And we can in fact show that the velocity um, which is given here, is related to the radius r naught squared. In the denominator I have the viscosity mu, this is the viscosity, and then I have the pressure gradient dP by dx. So, this is the relationship I am going to borrow from laminar viscous flow theory. Okay. Let us now look at, with this little background, let us look at what is going to happen in the case of tube flow. So, let me just take a tube, long tube, and I am going to have the pressure transducer here at one end, and the pressure to be measured is at the left end. Okay. So, this is a long tube. So, if I take a certain length L of this tube, because of friction, when the flow is taking place from here to here, we will later see why the flow takes place or why the flow should take place at all. We will come to that a little while later. When the flow takes place from right to left, from this side to this side, there is going to be a friction in the tube, and therefore, there is going to be a pressure drop, which I call as the pressure drop due to friction, delta P subscript F. This is identified with the pressure drop due to viscous flow. So, this will be due to laminar viscous flow. We will say laminar viscous flow pressure drop. Actually, the pressure drop will be negative. So, the pressure here is higher and the pressure here will be lower. That is, this is high and it is low. Of course, finally, the two pressures are going to be the same. Initially, there will be, when there is flow, there will be a pressure drop. So, the pressure at inlet will be higher than the pressure here. Okay. And we can show that dP by dx will be nothing but delta P due to friction divided by L. And this is going to go along with the expression between, if you remember, um. So, you can see that the mass flow rate is nothing but the density of the fluid rho m multiplied by the velocity of the mean velocity multiplied by the area of cross section of the tube, rho m um into A, this will be m dot. So, we will introduce an important definition here. So, we will say resistance of the tube due to friction. The analogy will be with Ohm's law. In electricity, we have the Ohm's law. The Ohm's law says that the current is potential difference divided by the resistance. So, we will identify the potential difference here with the pressure difference, and we will identify the current. Instead of the current, I have the mass flow rate. So, we will say that this is potential difference divided by current. So, this is an electricity. In fluid flow problem, we will introduce, this will be potential difference is pressure drop, pressure, and current will be mass flow rate. Actually, current is also a rate. It tells us how many charges per second are flowing through the conductor. The potential difference is the voltage across the conductor from one end to the other end, and that is how you get the Ohm's law. So, I am just drawing the analogy with respect to Ohm's law, and therefore, I will say that resistance R will be minus delta P f by m dot. This minus is to just take care of the fact that the pressure is changing, pressure is actually decreasing in the direction of mass flow rate. So, I want the resistance to be a positive quantity, therefore, I will say minus delta P f by m dot. All I have to do now is to combine the expression in the previous. If you remember, I have got u m equal to r naught squared by 8 mu dp by dx, and in fact, this dp by dx is nothing but delta P f by L. So, I am going to take this expression, and the second expression I have got is rho m u m into A equal to the mass flow rate. So, I am going to substitute here, and then number 3 I am going to substitute delta P f m dot and obtain the resistance. So, I will just give the expression. So, from the previous results, after some simplification, we can show that R will be nothing but 8 nu L divided by pi R naught to the power of 4, where nu is equal to mu by rho m. Okay. So, this is the concept of the resistance due to flow in a tube, which is in analogy with the Ohm's law of electricity, where the potential difference divided by current is the resistance, the potential difference is the pressure drop, current is the mass flow rate. So, the ratio of these two, of course, with the negative sign, because I want the resistance to be a positive quantity when the pressure is actually decreasing in the direction of flow. So, this is the important result I am looking for. This result will be used in various applications, and let us look at one of them, which is the case of transient response of a U tube manometer. Of course, we already know what a U tube manometer is. It consists of a heavy liquid or a liquid of suitable density, which is taken in a U shaped tube, which is held vertical in orientation, and one limb is connected to the pressure which is to be measured. The other limb is connected to the pressure which is a reference, maybe atmospheric pressure, maybe some other pressure. Essentially, the head or the difference in the height of the manometric liquid in the two limbs multiplied by the gravitational constant and the density of the fluid is going to give you the pressure difference across the two sides, and that is how you measure the pressure. So, a head is developed proportional to delta P, and that is the manometer head. So, it is essentially we are going to show that it is a second order system, as we will show in a moment. So, the analysis, how are we going to do that? It is basically the application of Newton's second law of motion to the manometer liquid as it oscillates within the tube. I am already foreseeing that the fluid is going to liquid is going to oscillate in the U tube. In fact, if any one of you has looked at a U tube manometer, you will see that it is going to oscillate when you suddenly connect the pressure to be measured, it will oscillate and then settle down. Finally, of course, it has to come to steady state when the head will become a steady value. Before it goes into that particular value, it is going to go through oscillations. So, the analysis I am going to show on the board by working out the various steps required, and let us look at how we are going to do that. So, let me just draw a schematic of a U tube. At any time, the fluid is like this, the manometric liquid is occupying this thing. So, at any time, this is the which is a function of time, because I am talking about transient. So, I am applying a pressure here, I am applying another pressure. So, delta P is the pressure difference between these two, and initially what I expect is that it is at the datum like this. Initially, this is initial, before we apply the pressure, and then once you apply the pressure, it starts going through motion, and I am capturing what is happening at a particular instant of time. So, let us look at all the terminology is the following. So, the length of the column, I will, this is the length of the column, the length of the manometric fluid. So, L is the length of the manometer liquid column. This is the total length, and we have H is the manometer head, which we have already talked about earlier. The area of cross section, you can have a circular tube, the area of cross section is A, and the fluid has the liquid has a density of rho m, and it has a viscosity which will be mu, and so on and so forth. So, I want to find out what are the forces which are acting on this fluid and the liquid at any instant t. So, there are actually 4 forces. So, we will say forces acting. When you want to write the second law of motion for the liquid, I have to identify all the forces which are going to be coming into the picture, and then I have to balance the forces. So, that is what second law of motion is all about. So, the forces acting, one is force due to acceleration, because the fluid is oscillating, it has got a certain velocity and certain acceleration. Force due to acceleration, this will be given by the mass of the fluid or mass of the liquid, that will be rho m A into L. A into L is the volume, rho m is the density, this is your mass. And we will assume that the height h is changing with respect to time, and the derivative which gives the acceleration is d squared h by dt squared. So, this is the force due to acceleration. So, let us look at the other forces. Second force, this is the force which is bringing about, force giving rise to the change. the manometer is changing, the liquid is oscillating only because there is an external stimulus to do so. This is given by the force due to the pressure, and that can be written as P into A. This is the pressure. So, this is helping the H to increase or change. Number 3, the force opposing the motion actually there are two forces opposing the motion, and therefore, I will say A, weight of the column H. You can see here that there is a this height of the column, it is applying a force in this direction, and H is trying to go up, whereas this is going to come in the lower direction, and therefore, there is a resistance to motion because of the weight of the column H. This is given by the density rho m, then A into H, this is your mass into acceleration due to gravity. This is your mass, not the total mass. Total mass would have been rho m A into L, which is for the entire column. Here it is only the extra height which you are having on the right side of the U tube manometer. B, viscous resistance, which we talked about a little while ago. So, let us look at this modeling a little more carefully, because it is somewhat confusing. What I am saying is, why is it confusing? I am assuming that the entire fluid, entire liquid in the manometer is moving to one side. So, one would assume that each point in the liquid is moving up with the velocity equal to dH by dt. dH by dt is the velocity of the liquid. I am assuming it is incompressible, therefore, the velocity is dH by dt. And now, how does the viscous friction come on top of that? So, that is the main problem. So, I am assuming that when it is moving up, it immediately goes into the fully developed flow, which is an assumption. So, that actually it is moving up with a parabolic velocity profile, but I am looking at two things: the mean velocity, dH by dt I will call as the mean velocity. There is a velocity profile in the tube which is due to this viscous effect, because the central line of the tube, the velocity will be higher, the velocity at the sides where it is in contact with the surface of the tube is 0. So, it is moving with a, so it is a, let us look at it as a simple modeling thing, because everything ultimately comes into how we look at it. I am not saying that this is exactly what is going to happen. What is happening is something, how I am describing is this way. Okay. So, with this background, let us look at the resistance due to viscous resistance, that will be given by the definition of resistance. We know that resistance is equal to the pressure drop divided by the mass flow rate. So, the pressure drop multiplied by area is a force. So, what I want is delta Pf multiplied by the area of cross section. Okay. So, viscous resistance is nothing but delta Pf multiplied by the mass flow rate I am sorry, not the mass flow rate, the area of cross section this is what I want, delta Pf into area of cross section is what is required, and this will be nothing but delta Pf is m dot into r by definition of the resistance multiplied by the area of cross section. So, if you look at the, I can say this is 1, this is 2, this is 3, this is 4. So, there are 4 forces. The second law of motion will tell us that the net force will be the net positive minus the net negative. So, we have to take into account the forces which are helping the motion to come about and the ones which are going to prevent the motion from taking place. So, I will write the Newton's law for the moving liquid column. This is what is force balance. So, I have A L rho m d squared h by dt squared. This is the acceleration, net acceleration force. This should be equal to positive minus the negatives. So, we have P into A minus rho m into A h into G minus the viscous force m dot or A, and m dot itself is the mass flow rate is given by rho m into area into velocity. Velocity I will write as dh by dt, again using our idea of the modeling which I discussed a little while ago. Okay. So, I am going to substitute this in here. I am also going to do the following. I am going to divide throughout so that the equation comes out in a nice way. So, I am going to divide throughout by rho m into G and rearrange. The student may verify this after doing this particular thing. So, I will get the following equation. I will get L by G d squared h by dt squared plus R A by G dh by dt. This term is going to come here after I introduce this term plus h, that is this term, equal to P divided by rho m into G. So, this is the equation which governs the variation of h. So, what we notice is that it is a second order differential equation, and if you remember what we did in the case of a thermal system, we had a first order system there. First order system is governed by a first order differential equation. Here, because the equation is which is governing the problem is a second order equation, the U tube manometer liquid is a second order system. Its motion is governed by a second order differential equation, because this is nothing but the application of the Newton's laws of motion, and Newton's law will automatically bring in the second derivative, and that is what is happening here. It is the height which is varying with respect to time, and the equation is given in this form, and usually the equation written in a slightly different form which we call as a characteristic form. So, what we will do is we will define some new quantities so that it comes out in the, for example, if you look at the, we have L by G d squared h by dt squared. Okay. L as units of meter, I am talking about the L here, G has got meter per second squared, this has units of second squared. So, L by G is a square of a characteristic time. If you remember, we had in the case of a first order system, we had a characteristic time, we called it the time constant of the first order system. So, here we have a characteristic time, of course, L by G is a square of a characteristic time, or if I take square root of L by G, it should be a characteristic time. I remove the square, it is simply the characteristic time. So, I will call this as tau. Okay. Then we will also introduce what is called a damping ratio. In applied mechanics, you would have come across the vibration problem. You would have come across an equation similar to this. This is actually the vibration of a damped system, spring mass system with damping. The first term is the acceleration term, the second term, which is proportional to the velocity dh by dt, is the damping term, and the damping comes because of the viscosity. In this particular case, laminar viscous flow will give rise to a linear damping, and then the third term here is the displacement, and the spring constant is going to come here. Of course, the spring constant is not appearing here because in this case I have L by G which has gone into this particular thing. So, you would have had a spring constant coming in the term corresponding to this displacement term. So, the three terms here, this will be the acceleration term, this is the damping term, and this is the spring term, and the right hand side what you have is the forcing function. So, the analogy is very complete, and what I am doing is I am going to just introduce the damping ratio, which is usually given the symbol zeta. We will say 2 zeta tau is equal to R A by G. So, this is what I am introducing, but I am introducing in terms of the other quantities. Actually, if I substitute the values, you can see that zeta will come out to be R A divided by 2 square root of L G. R is the resistance, viscous resistance, A is the area of cross section of the tube, divided by 2 square root of L G, where L is the column length of the liquid and G is the acceleration due to gravity. So, if I introduce all these things into the equation governing the problem, I will get the following. So, I will get L by G will be tau squared. I am going to remove that, and you see that finally what happens is that the equation governing the problem tau squared d squared h by dt squared plus 2 zeta tau dh by dt plus h is equal to p by rho g m. I will write it as k p multiplied by p, where k p is nothing but 1 over 0. So, this is the final form of the equation. This is the final form of the equation, and this is second order equation, and depending on damping I can have different cases. We can have what is called under damping or under damped. We can have what is called critically damped, or we can have the over damped case. Over damped case, 3 cases are possible. So, what is the what are the differences between these cases? In the case of underdamped system, the liquid is going to undergo periodic oscillations. Flow is periodic, that means it will go up and down, and then finally settle down. In the case of critically damped system, it will just approach the steady state value from the one side. Okay. And over damped case also it is similar. The over damped case, it will take a long time for the value to settle down to the steady state value. So, this can be seen from the figure I am going to show on the one of the slides. This slide seems to be slightly, I think it is okay. So, we have a second order system. We are talking about what is called response to a step input. This is just like what we had in the case of a first order system, thermal system, when we suddenly change the temperature of the surroundings. Here, for example, initially the pressure is the same on the two sides of the U tube. Suddenly the pressure on one side is taken to a value equal to 1. This is the value. This dashed line shows the input or the step input in this case. I think the numbers here are not very clear, but I will just read them out. On the x axis or the time axis, what I have done is I have taken the ratio of t to the characteristic time, t by tau. I have plotted t by tau along this axis up to about 10 I have taken, 0 to 10. On the non-dimensional pressure, which I call as h divided by Kp into P, this is non-dimensionalized with respect to the forcing function. Kp into P is the value which is input, h is the height of the column, and if the system were to have very fast response, it would immediately go here and show this value. Of course, because the system is damped, whether it is under damped or over damped, certainly there is a damping. So, what happens is the under damped case, in this case I have taken zeta equal to 0.5, which corresponds zeta less than 1 corresponds to under damped case. You see that the function goes up, the pressure goes up, the height overshoots and goes to about 1.2, a little more than 1.2, you see that about 25% more, then it slowly comes down, it goes below, and again after 10 time constant it is just about to settle down to the steady state value. Critically damped, it is very fast response, faster than in the under damped case, but it never goes to the positive side, it just goes here, and at about a value equal to 4 or 5, it has already become very close to the steady state value. In the case of over damped, you see that it is going to take a long time. Even here it has not reached that value, it will take a long time for it to reach the steady state value. So, what does this particular figure indicate? It indicates that the damping of the system is going to play a very significant role in determining the behavior of the system. To understand this further, let us look at go back to the board and look at the parameter zeta is this parameter is going to determine the damping. And if you look at the previous, this is what is going to determine the damping. This is the damping parameter is this. If it is less than 1, it is under damped, equal to 1 critical or critically damped, greater than 1 over damped. So, the important parameter which is going to determine that is this R, the fluid resistance. And if you remember the fluid resistance, if you go back, we can see that I think I have to go back one more. The fluid resistance is 8 nu L divided by pi r 0 to the power of 4. So, it depends on the viscosity viscosity depends on the liquid. So, the liquid you take inside the U tube is going to be an important parameter, its property. Number 2, it depends on the geometry. Geometry depends on the length of the column and the radius of the tube or the area of cross section. And you see that there is a r 0 to the power of 4, r 0 to the power of 4. If you take smaller and smaller radius, the resistance becomes larger and larger, and therefore, if you take a U tube manometer with very small diameter for the U tube, you will have possibly overdamped condition. And again, if the length is very long, if you have a very large column for the liquid in the manometer, you are going to have a large resistance, because L is occurring in the R here. Okay, the long length and small diameter are going to drive it towards overdamped condition, and of course, viscosity is also going to play a role, may not be very major, but the major role is going to be due to the length and the radius of the tube. Normally in practice, we take a manometer tube maybe a few millimeters diameter, 3 to 5 millimeters diameter, sometimes a little more. So, the diameter is going to be about 3-4 millimeters. The length of the column is determined by the density of the material of the liquid and the largest pressure you would like to measure. So, if you remember, the largest pressure you can measure is determined by the head difference between the two sides of the U tube column. Okay. So, if you want to measure a certain pressure, that determines the length of the column, because that is related to the height which you want to measure is related to the length of the column. So, you require a long length if you want to measure a large pressure difference, and therefore, the design of the manometer will require the choice of the material or the medium which is used as a manometer liquid, maybe mercury, maybe water, maybe some other liquid, then the length of the column, and the diameter is normally, as I said, is going to be determined, be chosen in terms of a few millimeters. So, you see that already the characteristic of the U tube manometer is decided once we have determined all the, or decided to have these particular parameters chosen to have certain values to meet with the requirements. So, what I will do is to take an example and see what happens. So, we will take the example of a U tube manometer and see how to look at the transient behavior. So, this is example 25. So, your mercury U tube manometer it has a total length of 60 centimeters is the column length, and maybe we can see if 60 centimeters is the total, roughly 60 centimeters of the tube, the liquid height gives you the idea of the maximum pressure we can measure. It will be probably little less than this, okay. And it has a 3 millimeter diameter tube. We want to determine the period of oscillation and the damping ratio. The period of oscillation is nothing but the time characteristic time I spoke about, and the damping ratio we want to determine for in this case the liquid is mercury. And I also want to find out what happens if the manometer liquid is water at 20 degrees Celsius instead of mercury. If I change from mercury to water, what is going to happen to the time constant and also the damping in this particular case. Of course, time constant, as you saw earlier, is square root of L by G. It does not depend on the nature of the liquid. It depends only on the length of the column and the gravitational constant, and therefore, it is not dependent on the material of the liquid medium which is used as the manometer liquid. So, let us look at this problem. I will work it out on the board. So, this is the U tube transient So, I will indicate how the analysis is done by working out the details. We require to use the properties of the material we have to take from a handbook. For example, mercury properties we can get from a handbook of material properties. Nu is 0.114 into 10 to the power of minus 6 meter squared per second. I am taking everything at 20 degrees Celsius. And the density is 13,579 kilogram per cubic meter. We are already given data. L is 60 centimeters, I will convert it to meters, 0.6 meter, and R naught, I am given the diameter of the tube. R naught is diameter divided by 2, that will be 3 millimeter divided by 2, 1.5 millimeters, and I will write it as 0.0015 meter. So, this is the half of diameter. Because if you remember, the resistance is calculated based on the radius of the tube and the length of the column. And of course, we will take G equal to 9.81 meter per second squared, which may vary slightly between different places. So, it may not be a major parameter to worry about, the variation may not be very important. So, I can calculate immediately the time, the characteristic time is square root of L by G, square root of 0.6 divided by 9.81. This comes to 0.247 second. So, the length of the column is 0.6 and the characteristic time for the system is 0.247 second. So, this is the one answer we wanted, we will call it A. The next answer is we are interested in calculating the tube the time constant is here, or the characteristic time is here. We want to find out the damping ratio, that is the other parameter which is going to characterize the system. So, to calculate the damping ratio, I need to calculate the various things which are going to go into that expression. So, the liquid resistance R is given by 8 nu L divided by pi R 0 to the power of 4, 8 into nu is 0.114 into 10 to the power of minus 6, length is 0.6 meters divided by pi into 0.0015 whole to the power of 4. This is given by 3.441 into 10 to the power of 4, units is 1 over meter second. You can figure out the units, 1 over meter second. So, the area of cross section of the tube is pi R naught squared this will be 7.069 into 10 to the power of minus 6 square meters. All these are required in calculating the value of zeta. So, the damping ratio zeta is nothing but R A by 2 root G L, and I just plug in the values R into divided by 2 square root of 9.81 into 0.6. This comes to 0.0501. So, the damping ratio has come out to be 0.0501. What does it mean? It means that it is underdamped because it is less than 1, therefore, we have an underdamped system. If you observe a mercury in a tube, U-tube manometer, you will always, you will most invariantly you will see that it is going to be an underdamped system, and if you subject it to a sudden application of pressure on the side, it will go through a lot of oscillations. That you will be able to see if you do a simple experiment with a U-tube in your laboratory. And in fact, that is the answer B which was required in our problem. So, the next one, if the liquid is water instead of mercury, I will not go through water instead of mercury, only change is nu, is the only thing which changes, and of course, if you want rho also are the only things that change. Of course, the change in the density is important because the U-tube now will measure much smaller pressure difference across the U-tube. The head corresponds to a much smaller pressure. So, all I have to do is to recalculate the values using nu for water at 20 degrees Celsius is 1.006 into 10 to the power of minus 6 meter squared per second. Of course, the density is also smaller, it is about 13 times smaller than the other density of the other one. So, in fact, I can calculate R is proportional to nu, and therefore, this will come to a value of 3.036 into 10 to the power of 5, resistance has changed, this is again in 1/meter second, and the parameter zeta becomes 0.4424 less than 1. It is still underdamped, but it is much more damped than the case of mercury which we saw earlier. So, in the next lecture, what I will try to do is to look at the two other types of pressure measurements and look at how to calculate the or how to look at the transients in those systems, and then also look at a example to get an idea of the quantities which are involved in such cases. Thank you.